Hello and welcome to this session of inorganic chemistry. We had completed hydrogen and its compounds. And now the turn for alkali metals. That belongs to group 1 of the periodic table and belongs to also S block, the left portion of the periodic table. And as you know, our method of learning inorganic chemistry will be PowerPoint presentation based. Less of writing, more of understanding, and the notes you have to write at a later time. You write everything what I will be explaining to you in your copy. Unless you write it as a beginner, you can't benefit. I can tell with conviction. You have to write the equations, you have to balance them by applying some of the good methods like ON method if it is a difficult redox reaction equation, right? Now, these are the group elements, alkali metals, lithium, sodium, potassium, rubidium, cesium, and the radioactive francium, and the elusive new element that has been attempted several times to make it long-lived for some time to study the properties, yet with no success. But they are confident that within a short time, they will be able to discover the next alkali metal below francium, as they used to call eka-francium. But now it has been named as Untitled 119, and that is not yet discovered. That will be a synthetic element, a very heavy element, and it may not have similar properties. It might have many dissimilar properties with alkali metals. It will be very, very heavy. Let us forget about Einsteinium. Francium is a beta emitter. It belongs to the actinium series, and this by beta emission is converted to radium. Radium again is an alpha emitter. It goes on in a series. Forget about that. So francium is a beta emitter having half-life period of only 22 minutes. Now, the electronic configuration of all these metals is NS1, where N varies from 2 to 7. When N varies from 2s1 is lithium, 3s1 is sodium, 4s1 is potassium, and so on. And it is francium, it is 7s1. Then the 8th period, which is about to start with Untitled, will be 119. That will go to 8. Now, oxidation state is always +1. Only one electron that will be knocked out to form ions easily. They have the lowest ionization enthalpy in the respective periods, so they form positive ions easily. And they are very shiny. You can make it a shiny white silvery metals with a luster. But that is, you find it when you freshly cut it by a knife, because they are very soft. But the color very soon tarnishes, it blackens due to surface oxidation. That is called corrosion. That corrosion becomes faster as you go down the group, the reactivity increases. So blackening becomes faster and faster down the group. Cesium being, you cut cesium, within an instant it will become black because of aerial oxidation. Now we'll see what products will be formed due to the oxidation later on in our program. Cesium is the only exception. It looks golden yellow. Others are silvery white. They are soft metals, can be cut by a knife, and the softness goes on increasing down the group. All are soft. because their metallic bond is weak. They are the bulkiest atoms in their respective periods. So the metallic bond is the weakest. And hence, the interatomic cohesive force, the metallic bond is weak, and therefore you can apply a little bit of force in a knife to pierce into two parts. And the softness increases as the metallic bond becomes weaker down the group. As size increases, you can cut it more and more easily. Now coming to, I'm telling you how the Untitled experiment was done, and it's been very difficult to get Einsteinium, which is also a synthetic element in the actinide series. 254 is the mass number. That is a synthetic element. And when you bombard with calcium in a synchrotron and super synchrotron device, this as a projectile will enter into the tummy of Einsteinium, and that will produce the new element, so-called Untitled, but it has not been found to be stable, could not be isolated. But possibly this is one of the methods by which you can get this element. Forget about that. Now coming to atomic size and ionic size, guys, you are quite thorough now. When you are studying alkali metals, you are thorough in periodic properties in your 11th class program. I mean, you are still in 11, and in the periodicity program, you have done everything in a very systematic manner. So atomic size and ionic size increases down the group. Of course, the cation is smaller than the respective atoms. By removing an electron, the effective nuclear charge increases. So there is a shrinkage in the size. But systematically, it goes on increasing down the group, whether it is a neutral atom or a monopositive cation. Melting point, boiling point also decreases systematically down the group because the metallic bond becomes weaker. Not only the softness increases, but also the melting point also decreases, the boiling point also decreases. Density is nothing to do with the metallic bond strength. It goes on increasing, it becomes heavier and heavier. Now, the only exception is that potassium is little lighter than sodium, but it goes on increasing. As I told you, that mass increases more disproportionately compared to the volume. So the net effect is the increase in density. And of course, down the group, there is a very peculiar effect comes in that is called the relativistic contraction effect. That makes it super heavy. I mean, Untitled is believed to be super heavy, right? So the density goes on increasing down the group. I'll show you the table, the physical data table, to have a glance into all the data. The ionization enthalpy at the lowest in each period. Therefore, it is easier to knock out the electron. And therefore, all the alkali metals, they are available in nature in combined states, not in free state. And ionization enthalpy goes on decreasing down the group as the size increases. Electronegativity are low values because they are electropositive metals. So the electronegativity values are much less than 2, it is 0.9, 0.95, like that. But that also goes on decreasing down the group as the electropositive nature, the metallic character, increases. Electron, in your class 12 program, you will know that all of these metals, they have a typical unique crystal structure that is called BCC. Body-centered cubic structure. And what is body-centered cubic structure? What is body-centered cubic structure? You will be knowing later on in your solid state program. So forget about what is BCC, not BBC, BCC. BBC is British Broadcasting Corporation. BCC, body-centered cubic. I hope now the network connection is good and you are able to hear me. Can you raise your hand to demonstrate that now things are going fine? Never mind, this is being recorded, and at any point you are unable to hear, you can, at that point, you can just watch the video and get it done. Okay, hands down, please. And boys and girls, if you are watching, this is a live class going on, and this will be a public video. And you please be with me to complete the general trends in the physical properties and chemical properties of alkali metals, the general trends, their group trait, similarity in their behavior, and the dissimilarities also. Now, conductivity is very, very high. Conductivity and electrical and thermal conductivity, they are high. I forgot to make it bold. I'm doing it now. So the thermal conductivity and electrical conductivity, they are metals, they have malleability, they have ductility, but they can't compete with transition metals. In the face of transition metals, the S-block elements, they are nothing. As far as malleability, ductility, thermal and electrical conductivity, they are concerned, may be high, but they cannot compete with transition metals. They are the best. Now, have a look to the data. The atomic size goes on increasing. This is an angstrom, goes on increasing from 1.52 angstrom to 2.65. The cationic radius also goes on increasing. Melting point goes on decreasing, while lithium is only 181. Cesium is so low melting that at summer, during summer, it remains as a liquid. So also rubidium. Cesium is only 28.5, say 29 degrees Celsius. It can melt on your palm if you keep it on a glove. It's very dangerously reactive, so don't hold it in your hand. Boiling point also decreases. The only energy is first ionization. There is no second ionization. Of course, you can pluck out the second electron, but that will need much greater, more than 5-6 times than the first one, because you are knocking out from the stable octet. Therefore, and in case of lithium, it is stable duplet. So the second IE are extremely large, much larger, minimum 5 times larger than the first IE. Electronegativity, they are 1 and less. Lithium is 1 and goes on decreasing. Density goes on increasing. Only thing, potassium is bit lighter than sodium. This you have to remember. And these three, lithium, potassium, sodium, these three, they are lighter than water. They are lighter than water, but they don't remain friend with water. If you put them in water, they will react immediately. But I'm saying they are lighter than water. This is standard potential. This is the reduction potential. I tell you, sound you, more the numerical value of the standard potential, greater is its strength as reducing agent. They are all good reducing agents. They can displace hydrogen even from water, even from cold water, very vigorously. And the numerical value of the standard potential will tell you the relative reducing power. So looking to this, you know that lithium is the best. Don't go away by the sign minus. You'll be knowing the details in electrochemistry later. But more the numerical value of the standard potential, more is its reducing strength. So lithium is the best. Can you tell me which is the worst among them? They are the best among others. I mean, in the entire periodic table, they are the best, because their Standard potential are quite high, nearing 3. But there is an anomaly. Just try to remember, this is the hit point in alkali metals. Their relative reducing strength order. Number 1 is lithium. And I'm sure you are quite with me with your rapt concentration, rapt attention. So this is number 1 as a reducing agent. And then number 2 is, this is bracketed. They're almost the same. For all practical purposes, we say potassium and rubidium, they are more or less identical strength in reducing. And then comes this one, cesium. This is same. Cesium, potassium, rubidium, more or less the same. And distinctly, sodium is the last. So, being the second element, it is among them is the least powerful reducing agent. We shall know why. These are more or less similar in their reducing strength. And lithium is the uncompromising first. The difference is quite large. So lithium is the best reducing agent. Coming to hydration enthalpy of their positive ions, M+. Obviously, smaller the size, greater is the hydration enthalpy. Because the charge density is high, it will attract more number of water molecules, and the attraction will produce a lot of heat. That is called the hydration enthalpy or hydration energy. That is maximum for Li+, minimum for Cs+. Now, let us look to their availability. Lithium is present in the ore called spodumene, sodium in several rock salt and other minerals, potassium as sylvite, rubidium, they're present in lithium minerals. Very, very scarcely, rarely, along with lithium minerals, they are present. And their abundance in earth crust is very, very less. This one. And out of this, potassium and sodium is more than potassium. Then it comes to rubidium, then lithium, and then the least available in the earth crust is cesium. And this is their order in the earth crust. The 7th most abundant element, this is the 8th, this 23rd, 35th, 46th most abundant element in the earth crust. Coming to their isotopes. Lithium has 2 natural isotopes. I have given natural isotopes, 6 and 7. 7 is more abundant, so the average is close to 7. For our calculation, we take 7 because it is close to 7. You know how to find out the average atomic mass. Sodium and cesium, they are monoisotopic. Their isotopic mass is same as their atomic masses. Potassium has 3 natural isotopes. Remember that. Out of which 39 is most abundant. 41 is least, 6.73. They are stable, but potassium 40, which is present in very small amount, is a beta emitter, is radioactive. So natural potassium also contains the radioactive potassium 40. But 39 and 41, they are stable. And the average is coming close to 39 because 39 is more than 90%. Rubidium has also 2 isotopes. One of them is 85, is stable, and 87 is quite appreciably large, 27.8% is radioactive, is a beta emitter. And the average is 85.5. So sometimes we take 85.5 as the average atomic mass of rubidium for calculation. Cesium is also monoisotopic. Now coming to the interesting part of the alkali metal and their compounds is the exhibition of a typical characteristic color. Lithium or its compounds, they produce in the flame crimson red color, and it absorbs, it emits. These are the emission wavelengths. These are the emission wavelengths. .8 nanometer that comes under crimson region. Then sodium and its compounds, they produce golden yellow, this nanometer. Potassium violet or lilac, rubidium purple, cesium blue. These are the coloration that are the emission spectrum that they emit during, when you heat it in a flame. Now the question arises, you might ask me a question. The reason for this flame coloration is that the only electron which is present in the atom will be excited by absorbing energy from the heat source, from the light source, light and heat. It will go to the higher level. And when it will de-excite back to the ground state, then it will show its emission. And each transition emission has a particular bandwidth. The delta E is different, hence their corresponding lambda values are different. So for atoms, neutral atoms, it is understandable. You take sodium metal from kerosene, as you know from your childhood days, these are stored inside kerosene, usually in petroleum oil, as they are highly reactive with all the components of air. So they are kept inside kerosene. So take sodium metal, put it in a flame, put it in a, hold it in a spatula or a tongue, and sew it in a flame. You will find a golden yellow color having two, lines, D1 and D2, but they are mixed, yellow color, golden yellow. But why sodium chloride will also give you golden yellow? You may ask me. Na plus has no electron. Na has one electron that will be excited and then de-excited to produce emission spectrum. But what about Na plus, which has no electron? Can the electron go from the stable octet? No, it doesn't. What happens really when you take sodium chloride, a piece of your table salt from your dining table, take piece, hold it in a tongue and sew it in a flame, you will find golden yellow. What happens? In the flame, the ionic bond breaks. Chloride ion, that gives the electron, the extra electron that it possesses, back to sodium ion, and now sodium becomes atom. There is no more ionic bond, becomes atoms. And that electron which is revived back, that goes to the higher state and returns to give the characteristic emission spectrum. You have to remember these colors. These are very important for your examinations. Please raise your hands if you are able to understand what I am saying. So I have requested you with all earnestness that you be integrated with me as I am trying to integrate with you. So let us make this class successful. Successful for your purpose. Undoubtedly, as an instructor, I will make it successful for my purpose. Now, you have already studied photoelectric effect. When you put a metal as a cathode and allow UV light or visible light to let fall on the metal, it will eject electron. It will remove the surface electrons, and those are called photoelectrons. And if you put it under a loop, under a circuit, then you will find current, the photocurrent. And the less the ionization enthalpy, better the metal behaves as a photoelectric material. So these are very good photoelectric material. And the best is cesium, because less the ionization enthalpy, better is the efficiency. Smaller is the amount of energy that the work function, the work function or the threshold frequency will be less. More easily it can be knocked out from the surface. And coming to hydration enthalpy, you already know that it goes on decreasing. As the size increases among the cations, it goes on decreasing. And that is the reason why the electrical conductivity is just the opposite. Li plus Ac is a very bulky ion. In the naked state, it is a thin ion. But in the hydrated state, it is the thickest ion and moves very slowly. So the electrical conductivity is the maximum for cesium plus, as I used to call it, is wearing a banyan, simply a banyan. But lithium plus is wearing a very thick coat that makes it so bulky, can't run faster, become the slowest person. Now, as I have already told you, here comes the most important part of alkali metals, is the reducing strength. We already know that lithium is number one, potassium, rubidium, and cesium. Let me not hesitate to concede to equalize this. These three are more or less the same, but convincingly, sodium is the least powerful Ra. Ra means reducing strength. And I have given you from that data table that lithium plus lithium, that reduction potential is minus 3.04, and the least among them is sodium plus sodium. Now forget about the negative sign at this moment. We are not discussing electrochemistry. Now, I will tell you that why it has happened like that. Why lithium having the highest ionization enthalpy. As a lay student, if you only focus on ionization enthalpy, you will say that lithium loses electron with utmost difficulty because it has among the alkali metals has the highest IE. Then how come that is losing electron most easily and is becoming the most powerful array? Which factor is responsible for it? I would like to ask you a question. Raise your hand. Which factor makes lithium to behave as the most powerful reducing agent, despite the fact that lithium has the highest ionization enthalpy? It loses electron with most difficulty among the alkali metals, although in general they have low IE in their respective period, being the lowest. Raise your hands. I take a break now for 30 seconds. If you are watching, any one of you is watching, then you also think this question is also meant for you. What makes lithium the best reducing agent? And those who are in my class now, the live going on, I would like to ask them, and you will hear the voice of the participant to answer. Doesn't matter if you answer wrong. Now, let me tell you some secret thing. Don't tell it to anyone. The secret thing is that the instructor, perhaps, I think in that way, perhaps, will be happy if you answer wrongly to a critical, difficult question. If you answer wrongly, then perhaps the ego of the teacher will be satiated. That means nobody knows. The teacher now then explains, getting the satisfaction that yes, I did something. I told something new to the students. So I'm just kidding. Try to answer. Here is the first hand is Miss Patnaik. Yes, I'm asking you to unmute. Ms. Patnaik?
So large amount of hydration enthalpy?
Precisely the correct answer. I'm so happy. I think others who have raised their hands would have answered the same. It is because the amount of energy released during hydration is quite high due to small size of Li+. That makes the process highly spontaneous and much more spontaneous than any other. So the property which bells out or which is responsible to make lithium first is the highest hydration enthalpy. Now, let me tell you the conversion of this the other way. Actually, this is happening when metal is acting as a Ra reducing agent. This is really happening. But we are measuring the opposite potential, just changing the sign. Because IUPAC has recommended to say electrode potential means reduction potential. But actually, it will not be unless you carry out electrolysis, a forced reaction. It won't. Spontaneously, sodium ion will not become sodium atom. The other way around, sodium metal will be sodium ion. So, to study what are the energies involved during the conversion of the solid metal from the kerosene to the hydrated iron, three energy terms are involved. First, you have to make it atoms. That is called atomization energy, or some people call it heat of sublimation. Sublimation energy or the atomization energy. That is positive. Means it is absorbed. So first you take the metal under kerosene and vaporize it. So the amount of energy absorbed is called the heat of atomization or the sublimation energy. That is positive. Then you pluck out electron from each atom to make it positive ion. That is called ionization enthalpy. That is also positive. And finally, the negative term, when the ions from the gaseous state will be plunged into the water, they get hydrated and produce a large quantity of energy. But the sum of these three energy terms is not negative. It is still positive because the positive terms are two in number. There are two positive terms. Negative term cannot supersede and make the net energy change negative. No, the net energy change is still positive, but the lowest this sum, the lower the sum of these three energy terms, which is positive, greater is the standard oxidation potential. And hence the reduction potential is the negative of that. And the lower reduction potential, that means the numerical value is high. We are more interested in the numerical value. But I told you that first we find the oxidation potential, which is really happening. It is plus 3.04. But according to IUPAC, we have to put in the table a reduction potential is minus 0.34 and say greater the numerical value or lower the SRP, stronger is the reducing strength. And if you do not look at the negative sign, you say greater the numerical value of the standard potential, greater is the reducing strength. So why this sum? Sum means the addition of the three energy terms becomes minimum for lithium and makes the oxidation potential highest and the reduction potential lowest because of high hydration enthalpy, which Ms. Patnaik has rightly answered. And then why sodium becomes the least powerful reducing agent? What is the negative factor which makes the sum of these three energy terms the maximum? That the sum is maximum means its oxidation potential is minimum, plus 2.87. Plus 2.71. But we have to write in a standard IUPAC format in the reverse manner. Reduction potential is minus 2.71. So the factor which makes sodium the last in the class is high sublimation energy. The unusually high sublimation energy, I think we have the data somewhere, the sublimation energy data. This is an hydration. Sublimation energy data is not here. The sodium metal has an unusually higher sublimation energy because of some of the crystal, quality. That sublimation energy is little unusually higher. So that makes the sum of these three energy terms the maximum. The sum is maximum means SOP oxidation potential is minimum. The sum is lowest means it is more easily this conversion can be achieved. If more easily the conversion can be achieved, so the standard oxidation potential is high. And if standard oxidation potential is high, standard reduction potential is low. That. Now we are going in a very fast speed. That is, extraction of metals are done by electrolytic method. And you may get a question, why chemical reduction method is not applicable for the S block elements and as well as aluminium of P block, the group 13, because they themselves are strong Ra. So using a less powerful Ra like carbon, like coke or any other metal is absolutely uneconomical. It is absolutely not economically viable. Penny wise, pound foolish. That is why the electrolytic method is the only choice to carry out electrolysis, pass electricity, and get the metals at the cathode. We'll be doing the individual chemistry of sodium, potassium later on. Today's program is general trends, which we shall complete. Chemical properties, you know, they are very, very reactive, stored under kerosene with water. The reactivity rate goes on increasing. Lithium is the least powerful. Cesium is dangerously most powerful element to react with water. You might ask a question. In the previous slide, we were talking that lithium is the best reducing agent. But why? What makes it the slowest person or actor in reaction with water? What makes lithium to react the slowest and cesium the highest? You can't put the same analogy. You can't say that lithium has a highest, just like, in politics, nowadays politics, the common man like us, we raise our hands whatever the majority says. Wherever the rain falls in a slanting manner in this direction or that direction, we orient our umbrellas in that direction. Here, often students say because lithium has the highest ionization enthalpy, it reacts the least, and cesium reacts the fastest. But you forget that the same three transitions are occurring. All the three, when you are putting a metal inside water, it is, surpassing all these three events. So how come you are taking only one, the middle one, by passing the other two? So it is a very, very opportunistic way of answering things. And that is wrong answer. It's not the right explanation. The real answer to this question, why lithium reacts the slowest and cesium the fastest, that lies in its chemical kinetics rate, nothing to do with thermodynamics. How much heat is liberated is not that, how fast. That is to do with the activation energy, not the enthalpy change. But the activation energy that you will study in your chemical kinetics chapter, class 12. So that, because cesium has very lowest melting point, 28.5, and this is 183. So it melts because you will find, you might have seen in different videos that now whenever you put a metal, alkali metal in water, it will immediately, it is a highly exothermic process. I have not mentioned here, plus a lot of it. And that heat immediately melts the metal. And the metal spreads. Once it becomes a liquid, it spreads throughout the surface. And more the surface area, more is the reactivity. That kinetics will tell you that the rate of reaction is directly proportional to the surface area. So since cesium has the lowest melting point, it melts very fast and spreads very fast. So the reactivity is the fastest. Lithium has the highest melting point. It melts slowly and doesn't spread out very fast. Hence, its reactivity is the least. That is the real reason, not to just bluff, taking the advantage of highest ionization enthalpy of lithium into account. You just try to satiate the examiner. So if I am the examiner, I won't give you any mark if you write that lithium has the highest IE, that is why it is reacting the lowest. No, I won't. With oxygen, see how interesting. Lithium gives monoxide, sodium gives predominantly peroxide. Of course, small minor quantity of oxide, but predominantly peroxide. But all the other three having large size, they give their superoxides. KO2, RbO2, CS2. Sodium gives peroxide. Remember, this is very important. And lithium gives monoxide. You might be wondering why. Because when oxides are formed, the metal ions and oxides, they should match in their sizes to get a stable crystal. So since lithium ion is very small in size, so two such ions fit well with one oxide ion. Sodium ion 2:2, that is 1:1. But others are bulky. If you become little obese, then more obese, less obese, doesn't matter, you are obese. And so all the three which are obese, one such ion require two oxide ions to have a good fitting, good matching, size matching to give you a good crystal. If there is a large disparity between positive ion and negative ion, the solid crystal becomes very, very unstable. That's the nature makes the composition of the oxide in a manner that the crystal becomes stable. That is why lithium monoxide, sodium peroxide, other three superoxide. And you know that superoxides are paramagnetic while others are diamagnetic. Superoxides are paramagnetic. O2 1 minus, O2 1 minus. They are they are paramagnetic and has only one unpaired electron, and they're colored because of the unpaired electron. It is colored. And I'll just take a break. I'll just drink a cup of water. You just look to this for fun. That we might have seen.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a light flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the route. Let's try cesium, our fifth alkali metal.
So cesium is so dangerous, it will break down all the container, so it reacts the fastest. Now, this you might be wondering that why I showed you behaving as if you are a class 8 student. We are showing this to class 7, 8 students, but I wanted to take a break. Right. Now, let's talk about the nature of oxides. These oxides, they produce hydroxides. If you have an oxide, immediately it will form hydroxide with water. And these hydroxides are crystalline solids. They are deliquescent, they absorb water and be soluble in it. They're called deliquescent. The sodium hydroxide bottle you might have seen, if you open it for some time, it becomes just like a liquid. It absorbs water and dissolves. Peroxide, when dissolved in water or some dilute acid, produces hydrogen peroxide. This -1 oxidation number, -1. I can annotate. That's the best part, that I got back my lost annotation. This is -1, this is -1. So this is a non-redox reaction. And when you take a superoxide, KO2, rubidium peroxide or cesium, superoxide, potassium, rubidium, cesium, superoxide, then when you treat it with water or with any dilute acid, then it not only produces peroxide, but also oxygen, where you can rationalize that oxygen is in the -½ state. It is superoxide, -½ and that goes to -1 here and 0 here. That is a disproportionation reaction. It's decreased and increased, right? This is superoxide. And with other non-metals, it sulfur, it forms sulfide. But with excess sulfur, remember that with excess sulfur, I would like to, use this. With excess sulfur, it produces polysulfide. For example, sodium with excess sulfur, if you heat, I have not given the heat symbol anywhere. These are all heating. When you heat it, it will produce pentasulfide. It's not a normal sulfide. It is a polysulfide where S5 2-, so that sulfur has an average atomic mass of -2/5, right? So with excess sulfur, these metals can give their polysulfides, but with limited sulfur, it will give their sulfides. And with nitrogen, there will be no reaction, except, remember, the only exception is lithium that reacts with nitrogen. Even in lithium, the corrosion coating that, blackens the surface of lithium is not only lithium monoxide, but also lithium nitride, because lithium is the only element in alkali metals which can react with the nitrogen. So this, and others, they do not. And with phosphorus, phosphide. It's very simple. Now coming to halides, this is the most important point in the entire alkali metal properties. The most important, not only important as the sake of knowledge, but also for the examination purpose. Now the formation of the solid metal halide, the sodium chloride or rubidium chloride or rubidium fluoride, these are all exothermic processes. The heat of formation, the enthalpy of formation from their respective elements in their standard states is negative. But these three, they have appreciable covalent character. Lithium halides, they have appreciable covalent character, excepting lithium fluoride, which is ionic. Others are predominantly covalent, so much so that they are appreciably soluble in organic solvents like ethanol, acetone, ethyl acetate, and many others. You know, for metallic fluoride, remember, this enthalpy of formation numerically decreases down the group, because fluoride is a very small size anion. So for that, remember the process, this process, the numerical value goes on decreasing down the group. Lithium fluoride has the highest value because its lattice enthalpy is the maximum. So it goes on decreasing, and but for other halides, for chloride, bromide, iodides, for you take metal chloride, lithium, sodium, potassium, rubidium, all chlorides, you will find the numerical value will increase because they're large size. They're obese. Of course, chloride is not obese. But yes, chloride, bromide, iodide, they come under obese. They need to do something to reduce the body mass and to make the body mass index befitting. So for them, the trend is opposite. It goes on increasing. The numerical value, all negative. They're all exothermic, but the numerical value increases for chloride, bromide, iodide, with the only exception that for bromide only, not for chloride and iodide, for bromide only, rubidium bromide, which would have higher, according to the trend for others, higher the heat of formation, it has a lower heat of formation than KBr. So you must remember this very, very mindfully, carefully, that the heat of formation for all negative, and for fluorides, the numerical value increases down the group, and for chlorides, bromides, iodides, independently, as you go down the group, the numerical value increases, except for bromides. In case of rubidium and potassium, the trend is opposite. Now again, for a given metal, the numerical value of heat of formation is maximum for fluoride and minimum for iodide. Is understandable because fluoride ion is the smallest in size, the lattice enthalpy is the maximum. So most energy is released from fluorides. Now the boiling point, same trend. Fluoride has the maximum. For a fixed metal, alkali metal, fluoride has the highest melting point or boiling point, and it goes on decreasing. They are all soluble in water, but remember, it's very important, is lithium fluoride is, even if it is an ionic compound, it is sparingly soluble in water. Sparingly soluble. Because, you know, that I told you, I don't remember, in thermodynamics, I told you, I think I did tell you that the solubility, it depends on the delta Z factor. The lowering of free energy is required. Now that many times it doesn't happen because the entropy term, even if is very, very encouraging, the entropy increases. That is an encouraging factor for spontaneity. But the heat of solution, the sum of the lattice enthalpy, which is positive here, unlike the case of formation, that is negative. But here, during solubility, lattice enthalpy is positive, and then hydrogen enthalpy is negative. So the sum of the two, that will give you the heat of solution. That is in most cases positive. But the entropy factor makes, you know, the total negative. That is why most metal halides, they are soluble in water spontaneously. But if you find that lithium fluoride is not soluble, the so-called insoluble, actually we call sparingly soluble, because we'll study in our ionic equilibrium chapter that the heterogeneous. The heterogeneous equilibrium, we will find lithium fluoride is sparingly soluble because, you know, it has got high lattice enthalpy, lower hydrogen enthalpy. The heat of solution is so predominantly positive that entropy factor is also not able to make delta G negative, and hence it is a non-spontaneous process. So also cesium iodide here, you know, it's both the hydrogen enthalpy is very, very less. Both are bulky. obese, positive ion, negative ion, both are obese. So these two, this is really sparingly soluble, but this is very less soluble. Besides these two, other halides are highly soluble in water. And the solubility goes on decreasing in the organic solvents, because as according to Fajan's rule, you know, as the size of the anion increases, the covalent character increases. And as the covalent character increases, the substance becomes less and less soluble in water and more soluble in organic solvents, weakly polar or non-polar solvents. The Fajan's rule will tell you why lithium iodide is predominantly ionic, predominantly covalent. But all the three have covalent character, appreciable covalent character. The covalent character increases highest in lithium iodide. So much so that you can address lithium iodide as a covalent compound. It's nearly 50% covalent. Right. Now, hydrides, we are almost at the end of our program. I would like to quench your curiosity. Might be how many slides we have to cover. So now we are here. This is the second, this is the third. This is less important. Then anomalous properties of lithium, how lithium is different from others. And then diagonal relationship with magnesium. And then that's the end of our program. So we will not make it a second lecture. Right? Raise your hands. Who want that this should be finished in one go? Sometimes I ask the participants some questions to make sure that the participants are not, in a peaceful slumber. They are not in a peaceful slumber. They are active and they are integrated with the instructor. That is me. Now, hydrogen can react with the metal. When you heat the metal with hydrogen in the gaseous state, it will produce ionic hydrides, where hydrogen is -1 oxidation number. And here, the reactivity is just the opposite that you found in water. In water, lithium is the least reactive and cesium is the most reactive. And the explanation I gave you is not the cheating IE, but the melting point, the kinetics, the spreading of the metal quickly in the liquid state. But here, there is no liquid water, no hydration. Simply, it will take up the ionization enthalpy. So since, yes, here, the point why lithium reacts, why lithium reacts the fastest, I withdraw. Even if it is a highest IE, but the crystal, the solid, this is solid, has the highest, the lattice enthalpy. So the total amount of energy released is more. IE may be the highest, but this lattice enthalpy makes lithium to react fastest. Cesium the lowest. It is in the gaseous state, not in the liquid, aqueous state. So remember, with a lot of caution, that there lithium was the slowest, but here in the gaseous state forming hydrides, lithium is the fastest. Now with liquid ammonia, this is an important point. With liquid ammonia, once you put metal in liquid ammonia, it will be forming an intense blue colored solution. That blue colored solution will contain the ammoniated metal ion, just like solvated. This is solvated. In water, it is hydrated. In ammonia, it is ammoniated. In general, solvated. So X number of ammonia, they are surrounding the metal ion, and Y number of ammonia molecules are surrounding the electron. So it will contain, the blue solution will contain ammoniated metal ion and ammoniated free electron. So these electrons are free. And therefore, these intense solution has three characteristic properties. They are not only strong Ra, because free electrons are available, and they are paramagnetic because of free electrons, and they are highly conducting because of free electrons. Just like metals, they conduct. They conduct in two ways, with the help of metal ions as well as free electrons. So this is a very, very interesting solution, intense blue solution containing ammoniated metal ion and ammoniated free electrons. But the moment you add some impurities or you wait for some time, then there is a reaction. You add some iron, powder, platinum or ferric oxide, then there will be vigorous reaction, no blue color, no paramagnetic solution, no intense blue solution. It will form this hydrogen gas and form the amide. It's not organic, you can't call it amine. In inorganic, we call it metal amide, where the metal goes from 0 to +1 and hydrogen from +1 to 0. This is a redox reaction, right? So this is metal amide. Only when you add some impurities, some catalysts, or you can wait for a longer time, then there will be slow reaction to give you hydrogen gas and the blue color will vanish. Now coming to carbonates and bicarbonates. The carbonates are all stable because the size is so matching that they don't have any interest to break down the friendship. You don't get anything when you heat this, but lithium, there is a size mismatch. So it is very, very, susceptible for thermal decomposition. I have not given this sign, the delta sign, giving you heat. So only lithium carbonate breaks down to lithium oxide and carbon dioxide. These are resistant to heat. Bicarbonates decompose to produce their carbonates, carbon dioxide and water. The only exception is lithium bicarbonate is not to be recovered in the solid state. It is unstable and only it can exist in aqueous solution. In situ, you can prepare, but you can't isolate in the solid state. Now, we are almost inching towards the end of our program. Alkali metals can form several alloys, like sodium potassium alloy is a liquid. Can you believe? Sodium is a metal, potassium is a metal, but sodium potassium alloy is a liquid because the size mismatch. Sodium is thin, coming under good BMI, body mass index, but potassium is obese. So they don't match well and therefore they don't form solid crystal. So it's a liquid and used as a coolant in nuclear power plants. Sodium amalgam, potassium amalgam, these amalgams are made deliberately to reduce the high reactivity of alkali metals. Sodium lead alloy was used to prepare a very, very environmentally unfriendly material, tetraethyl lead. Ethyl chloride with lead while giving tetraethyl lead. This tetraethyl lead, or shortly called TEL, was used as an additive in petrol as an anti-knock additive to reduce the knocking effect of that petrol in the engine. This additive was being used, but since the lead pollution becomes unbearably high, then now unleaded petrol is being commercialized, where no lead you will find as an additive. But that was history. History has to be discussed. You have studied history in your school. That is history. Now coming to anomalous properties, lithium is different. Being the smallest member of the family, it has got many unique properties, like it can react with nitrogen to form nitride, while others won't because of size mismatch. Lithium carbonates, lithium nitrate, lithium hydroxide, they are unstable to heat. Lithium carbonate will give carbon dioxide. Lithium nitrate will give you the reddish brown gas, NO2 as well as O2. But other nitrates will break down to form the corresponding nitrides. No reddish brown gas. Lithium hydroxide will decompose to give you water and lithium oxide. But no other hydroxides will give you their corresponding oxides that's stable to heat. Bicarbonate is only stable in aqueous solution. They're not stable in solid state. Also, it is the best RA. The fluoride, this is very, very important. You have to remember it. I will definitely ask you to note it with all seriousness. The fluoride, the carbonate, the hydroxide, the phosphate, these are sparingly soluble in water. Although they are ionic compounds, but because they're hydrogen, I'm sorry, they're, the solubility factor delta Z becomes positive. I told you the reason why the entropy factor is also not capable to make delta Z negative, because of high lattice enthalpy to break down. The hydrogen enthalpy is not sufficient. So these four compounds of lithium, they are sparingly soluble in water. It forms lithium monoxide, while others, they form either peroxide, sodium, and superoxide, others, obese. And lithium halides, they form hydrated salts. Because of small size, it can attract water and form hydrated crystals. Others, they don't. Have you ever heard NaCl.5 water, KCl.20 water? No. They are hydrated in solution. But once you crystallize, no water will remain. It will all go. But lithium chloride will give you a very stable crystal containing 2 water for each lithium chloride unit, like magnesium. So that these are the diagonal relationship with magnesium, because their sizes are same. Lithium plus and Mg2 plus, they have similar size. That is why they have many common qualities, like they both form nitrides. Both of their hydroxides and oxides are sparingly soluble in water. Both halides except fluoride have appreciable covalent character because they are small in size. Magnesium additionally has a smaller, sizes are same, I'm sorry. And high charge, of course, magnesium has another advantage of high charge. The polarizing power is more. So they are soluble in organic solvents, so they're covalent character. And both form hydrated salts, right? This is 6, I'm sorry, 6 water. That, I think, coming to the last uses of alkali metals, I told you that alloys, lithium lead alloy, I didn't tell that, lithium lead alloy used for making bearings for motor engines, and lithium aluminum alloy for making aircraft parts, lithium magnesium alloy for armor plates. Lithium deuteride is used for getting tritium for thermonuclear reaction. Fusion reaction, lithium deuteride is used to get tritium. Potassium chloride used is as a potassium fertilizer. Potassium hydroxide for getting soaps, and many alkaline reactions as catalysts. And it can also absorb carbon monoxide. Cesium as a photoelectric material. Rubidium, cesium as atomic clocks. Nowadays, the best timekeeper is being done by atomic level clocks. So rubidium, cesium, they are used for atomic clocks. Sodium vapor lamp giving you yellow light. Lithium ion battery, they are the most popular rechargeable batteries in electronic devices. And sodium, potassium, they have large biological importance. Although I'm not a master in this field, I can't authoritatively tell you about their real functions. But as a lay student of chemistry, we know that sodium and potassium ions, they are present both inside and outside all our cells. Sodium ion is responsible for transmission of nerve signals, regulating the flow of water across the cell membranes, and in transportation of sugars and amino acids into the cell. It is abundant outside the cells. On the other hand, potassium ion is abundant inside the cells, and it activates many enzymes inside the cell, participate in oxidation of glucose to produce ATP, and also along with sodium, it takes part in the transmission of nerve signals. It is abundant inside cell. And this is for a healthy human being. The outside cell will have 143 millimoles per liter of sodium and much small quantity of potassium. But inside cell, just the opposite. The potassium is more, sodium is less. So any deviation from this ratio, that will make human beings totally sick, particularly senior citizens. I can't say old people because age is a number. So the senior citizens, they often go for a syncopic attack. They fall down because of imbalance in sodium potassium. So it cannot be more than the prescribed level or less than that. So balancing, electrolyte test is being conducted in this routine blood analysis of your grandparents, particularly grandparents. And at the older stage, it is important that potassium sodium balance should be there. And this mechanism that operates in the cell is called the sodium potassium pump mechanism, operates across the cell membrane. And that we come to the end of our program. I think it is a little more than 1 hour. We started at 1:15, I guess, and now it is 1:25, 1 hour, 10 minutes. So I'm very happy that you guys, all of you, remain stuck to the program. Nobody has flayed away from my program. So I hope you have enjoyed the class. And if you're watching outside, I mean, not outsider, all of you are my close dears and nears. If you're watching this video, if you like it, don't hesitate to give a thumbs up. And if you are not still a subscriber to my channel and you are following our instructions, then why you hesitate to do that? Subscribe. Bye-bye. Take care. And next time, we'll be taking up the individual chemistry of sodium, potassium, and their compounds. Bye.